Good. Okay, great. Come on in, everybody. Come and settle down. And we have our first session of contributed talks. Can anybody hear me?
Use this one. This one's fine. We can use it on the board, so it was just muted.
Okay, that's fine. Yeah. Right. Okay, our first session of contributed talks is going to start off with Weixi, who's going to talk to us about F3, which is a compiler for feature engineering. So, take it away.
Thank you for the introduction, and thanks, Michael, for lending me his laptop. And okay, all right. So let's get started. I'm Weixi here. This is a work for feature engineering. We built a small language called F3. And it's great to be here. When I first saw the page of this workshop, I was thinking, oh, we should send our work to this place because, you know, functional programming working at Meta is probably a good sign of functional programming working in large, right? So, okay, this talk is organized around the three questions that you may have. One is, who are you? I think it's extremely important because, you know, when I was looking at any talk, I think usually, you know, how people come up to the solution is as interesting as, you know, if not more than the solution itself. So like people say, when the only tool you have is a hammer, then every problem becomes, you know, a nail, right? So I'm first gonna introduce what a hammer is, and then a little bit about feature engineering and how does functional programming help. Okay. So I went to graduate school at this pretty place called Indiana University. And when I was there, my advisor was writing this book called Little Typer. It's basically teaching high school students dependent types. And and that's kind of the cornerstone of the idea of this work. So I'm just going to quickly go into dependent type because probably everyone in this room already knows it, right? So, you know, just in ordinary functional programming, you can define this plus, you know, takes two numbers, x and y, it returns a number. So when you write this program, you do this case split, right? So if x is 0, you return the first argument, so on and so forth, right? Next, we can get into the kind of the gateway drug of dependent type, which is like proving plus is commutative, right? And so you can say we have two numbers, x and y, x plus y is y equal to x. Just as usual functional programming, we can do this case split. And here, for the first case, when x is 0, you know, we need to come up with something to prove it's correct, right? So the interesting thing about dependent types here, like as a normal human, when I'm looking at this, I think, oh, so x is 0 here, so probably what I need to prove is 0 plus y equals y plus 0. But actually, that's not what the compiler sees, right? So there is some evaluation underneath going on. So because of the way we define plus, like, you know, if the first argument is 0, then it automatically goes to y, not 0 plus y. So this is not what the compiler sees. Instead, it says something like this. So y is equal to y plus 0. So, I mean, we are still kind of far away from proving plus is commutative, but this is kind of the underlying idea. That is, the compiler sees something else. And this process is called normalization by evaluation, as people already know. And so the idea is, well, there's this kind of syntactic forms and the semantical forms, right? So there are, say, infinitely many different ways to express the same meaning. Some of them can be automatically reduced to a semantic form. Some of them may need some help. But the idea is, well, they all reduce to some semantic form. And when the compiler is doing something interesting, like program analysis, or like for the case of dependent type, it's checking whether two things are equal. But you can do something else. And something else is also based on this normal form. So that's a kind of the start. And next, let's talk about something that people in this room don't know. What is feature engineering? So basically, our compiler serves machine learning engineers. And this is my go-to example of explaining feature engineering to, you know, functional programmers. Let's say I want to teach a class about dependent types, teaching this language called Agda. And I can write a model to predict whether people will like my class or not, right? So this model, it needs to take some inputs. And so I need to come up some kind of signal to this model. So maybe how many lines of Haskell programs my student has written before, like, and then how many lines of induction proofs they have written, or maybe the number 3, do they like Unicode? So anyways, so so those are kind of the inputs. And one option you can do is, all those inputs, they are kind of from some database. What you can do is to dump all this input directly to your model. But usually that doesn't work very well. So what people usually do is to do a little bit massage here. Like, let's say I've been teaching Agda for many years, so I realized, well, maybe the line of code of Haskell and line of code of induction, they are kind of maybe the same thing. So before I giving 2 numbers to this model, I may just add them together and use them as one input. So this is kind of the essence of feature engineering. People just grab data from some database and do some manipulation of data. So as you can tell, this is usually done in a language called SQL. So that's kind of what we have built. All right. So let's see a concrete example. Like, say we have 2 tables. Like table I is a number of induction proofs. Table H is Haskell. And so usually, these data, they do not exist in just one database, not in one table. They exist here and there. So what feature engineering does is to load this, many different tables and combine them together. So this process of combining is usually done by this operator called left join, as you can see in line 3, T2. So what this left join does is, so here T0, we call it the main table, because after the left join, all the columns, all the rows still stay in the result table. And this T1 here is kind of the off table. And so sometimes after the left join, the off table, it loses some rows. So maybe, let's say, we have 3 students, XYZ. These are the induction proofs they have written. And this is, lines of Haskell programs written. This poor guy, Z here, just wrote too much Python or C++. And we add them together. So that's, by adding, we join them together. So you now see this new table with 3 columns: name, number of induction proofs, and the number of lines of Haskells. And we add them together, right? So this is a typical feature. And so maybe if I look at this result here, this person Z here, he wrote many induction proofs, but have a huge negative number of lines of Haskell. So I guess maybe since he wrote a lot of induction proofs, he's still hopeful. So what we can do maybe is to add a filter to filter out the kind of noise that impact our calculation. So let's say we just filter out everything that Haskell is smaller than 0. So what we can do is to add another node called filter. So this filter here is saying, okay, so for this off table, this T1, we only want the data where is larger than 0. So let's, for argument's sake, say 50 plus none is 50, but there's something, some other magic we can do. Okay. So this is one way to add this filter. You see, we first filter the T1 table, and then we do this left join. And maybe you can also filter after the left join. So it gives you a different result because, Z now gets filtered, right? So, okay, so this is one problem that we see over and over. That is, we have a compiler that basically transforms the feature in one form to another. So in order to optimize for the runtime efficiency, we often need to move the operators. So maybe sometimes this, and sometimes we need to break down a feature to multiple backend frameworks just for efficiency. So the first thing we need to solve is how do we validate the correctness? Like how do we know if the compiler is, a transformation is not like changing this table to this table? So that's the first question. And so when we have 2 graphs, if they are not the same, we want to tell, well, they are not the same. On the other hand, given the syntax of this, given the semantics of this left one, if we filter on the left table or the main table, it's actually okay to move it, up or down. It doesn't change the semantics; they are the same. So that brings another question. That is, we have a lot of features, like 100,000 of them running on a very frequent basis. So it will save a significant computation power if we can identify the sameness between existing features. So given two random features, maybe we want to identify, well, they do share the same computation at some point in the middle, so maybe we can just compute it once, and then, it saves some petabytes or megawatts. So this is the starting point of this work. One is to check if compiler rules are correctness preserving. The second is to identify the sameness between different graphs. Okay. All right. So as I said, when the only tool you have is a hammer, right? Every problem becomes a nail. So here's how functional programming helps. When I was looking at that problem, this is the exact picture that occurred to my mind. I was like, wow, this is a normalization by evaluation problem. Because you just compute the normal forms of those features or those SQL programs, and then you just check the syntactic equivalence, or maybe some people call structural equivalence of this feature. So that should be good enough. And then the first problem we are going to solve is, well, what does the semantic form look like? So, going back, so this is not a good way to do program analysis because there are just too many layers, just too complicated. We need something kind of flattened, kind of easier to be reasoned about. And so I was kind of thinking it's like a monad if you look at this thing here. So, a monad, it usually has, two parts, the more obvious, more frequently used part because of pure, and the less obvious, less frequently used because of effect. So here, basically, the pure is the columns that each feature provide. Like here, if you look at T3, it's providing, 3 columns, I, H, and N. And also, the effect part is kind of the data range. Like, if you look at this TF, this filter here, it's doing something implicit, like a side effect, right? So basically, the normal form contains 2 parts, the columns and the constraints. Let's see an example, actually the same example. When we are loading this table T0, it provides 2 columns. And along with those column names, we also have how they are computed. For example, this name here, it comes directly from this table I.name, and I is table I.I. And here the constraint is empty. We don't have any filter yet. The second table is equally boring, but the next one, when we do this left join, so this left join, basically it creates 3 columns, combining the one from T0 and T1. And a little bit trick we did here is if you look at this H here, it's coming from this table H.H, but we added kind of a little tag or some fake function called joined. It kind of reminds us, well, this H here, it was the off table of some left join, or maybe some off table of some left table of some right join. Anyways, it has passes this join, and it's possible that it has loses some rows. So it's different now. And also we added a constraint, which is those 2 names from those 2 tables, they must be identical, right? And the way I look at this, so the column part is kind of like, when you're writing an interpreter, you have this environment or variable bindings, like where does everything come from? Like what are their kind of normal forms? And so when we are computing, recursively going down, like here, this filter here, this T1.h, This H we know is actually a result of join. So in this, in the added constraint, instead of seeing table h.h is larger than 0, you see this, it's wrapped in this joined tag. And the select is kind of the same thing here. All right. So with this normal form in hand, we can just reduce all those programs to their normal forms and just do a simple comparison. So here, if you move a filter, on the right parent of a left join, then you result in a different normal forms like the left and right. But if you move the filter of a left parent, then they basically result in the same normal form. So there are many other different operators in SQL or F3, but they are all handled in this fashion. So basically, yeah. So that's the first thing that functional programming has helped, is to identify sameness. So either dedupe or for validation. The second thing, so after we have done the first part, we immediately realize, well, we can use these normal forms for something else, where people in machine learning or SQL, you recall it data lineages and data classifications or labels. So the idea is, well, models, they are effectively black boxes, so you don't know what's going on over there. But those features or those databases, they are the inputs to the models. So if the machine learning engineers are trying to, say, optimize their models, one angle they can use is to look at the inputs. Like if we know all the features, what kind of data is fed into my model and how they are transformed during this feature processing, then maybe it's easier for them to understand what their models are doing, right? So that's kind of the idea. But unfortunately, before we have these normal forms, the features is just a total mess, and it's very hard to connect the data to the models. So, excuse me. All right. So about this data classification problem, we just found a little type system, maybe very handy in this case. So let's maybe start with this expression. So that's something from our last example. So this n here is some table I and plus something else, right? So let's just, so what's its type? What's the type of n? Let's say, class is from two numbers to a number, and join is kind of the identity function. It says n is a number. And this is the least informative type annotation I have ever seen, and it's a number. It doesn't tell you anything at all. And when machine learning engineers look at their features, they also see this, and they have no single idea of what they can do with it. So what can we do? So because in the raw tables, let's say for one, we have name string, I is a number, and the other table is the same, right? So those are from the source tables. What if we kind of enrich the information we have with intersection types? So let's say for the name, we know they kind of represent some kind of ID. And this I and H here, they represent some line of code. So basically, you can just, people can come up with arbitrary constants as this semantic meaning or labels. So we can use this intersection type to describe something maybe more descriptive, right? So if we have those, then maybe we can run the type inference again, and n is still a number. So why is that? So it's because the way we define our plus function, it takes two numbers and returns a number. So I mean, say we already have subtyping, right? Then number intersects with line of code is still a number, so that's fine, a good input. But output is losing its semantic meaning. So a little trick here, what we can do is to extend our type system with bounded quantification. So basically, instead of saying you take two numbers, returning a number, you can say, well, we are taking now two variables here, A and B. They can represent anything, but they better be numbers. And as a result, we just return the intersection of both. So now we can automatically propagate or infer the information of the columns provided by a feature by using the people, like human-given annotations in the table. Okay, so let's see. So here on a low level, we know how each column is computed. Here, this table I is what people usually call the main table, and the table H is what people usually call the enrichment table, because it's using this information to enrich, to give more information to the other table. So basically, and then on the high level, on a more abstract level, we have some semantic annotations of each column. So using this, we have built kind of a database or knowledge graph or whatever you call it, so people can query all existing features. Like if someone is trying to write a new feature and they want to use this table I, so they can go ahead and query the existing, say, 10,000 features and ask, okay, so what other columns are usually used together with this table I.I? And we can return some information saying, maybe you want to use this table H because other people are using it as well. So that's one use case. And the other use case is we can check if people are using the columns they are not supposed to use. Let's say if someday this line of code becomes illegal to be used in some country, then we know, okay, so this is a feature that we should not run anymore. Okay. All right, so that's it. So using this, I know it still doesn't look very neat, but at least you can trace where each model have their signals coming from. So that's what we have done. Okay, so in conclusion, functional programming works very well in the large, and so we built this little Python DSL, and yeah. Okay, that's it. Any questions?
I'm curious to understand a little bit more about what's the distinguishing feature set of this DSL, and kind of what are the surfaces, what are the features you're trying to surface to the feature engineers? Mm-hmm. So it sounds like on some level it seems like, it's like a SQL engine. Mm-hmm. And I'm curious, like, is it like, how close is this dialect to SQL? Does it have like, is it importantly like different in its expressivity? Mm-hmm. And like when you're doing feature engineering, like examples of like interesting things you have to do, sometimes you have to deal with temporal features where you're like talking about the evolution of some signal over time, and you want to like include like distributional properties of the feature, so like you can like normalize them by their distribution. I'm curious if there's any of that kind of stuff here. Mm-hmm. And I'm also curious like how much of the kind of like optimization and analysis of this is kind of just what I would find from like a query planner in some other SQL dialect.
Good question. Thank you. So first, this project started as kind of a small extension of SQL. One motivation of making this DSL, I guess, was to have machine learning engineers write Python, which is considered better than writing SQL or C++, I guess, back in the days. And then gradually, we also discovered many use cases of feature engineering that are not SQL-ish. So there are some new computation paradigms, like you can actually invoke a model, or you can do some graph learning during this SQL engineering. So it's gradually growing out of SQL. So that's first question, I guess. And this is only part of the syntax. And also, I guess your second question is, there are many features. Are most of them just temporary, right? Or
this is a kind of about the expressivity question of like, how much time-oriented stuff do you have there? So you can do like, I guess the two features that were striking. One is asking things about the history of stuff and whether there's any special support for that. And then also distributional properties, like sometimes you want to normalize a feature by going from its looking at its standard deviation and then like adjusting it to some, I want, to pull things within some small, so that like within 2 standard deviations between 0 and 1, because like ML models, like neural nets are often like tuned to particular numerical ranges. And so sometimes when you don't just want to, all of these examples are like transforming like row by row, but sometimes you want to do transformations that have to do with an understanding of the full distribution of the data. And I'm curious whether any of that shows up in the DSL.
Yeah, good point. So first off, that's something we haven't started yet, but that's a very good point. And I guess since we have these normal forms, we also have the data range. And like something is larger than 0, we have those constraints. So yeah, I think it's possible to do that, and maybe. Yeah, we can definitely calculate some kind of distribution by using those constraints. But I guess eventually it's not a static problem. It's probably you have to run those features anyways to get the actual data, and in order to get an accurate estimation, I guess. Interesting question. Thank you.
If I understood correctly, you wanted this to, well, practically speaking, what are the benefits that people want out of it? One is, if I understood correctly, to share some of the computation by realizing that you keep doing this over and over for different features. So I guess, could you show us some performance benefits that this has led to? How much did you gain out of this?
Yeah.
And the second thing, I didn't understand the part about trying to clarify where the models come from so that the modelers know. Is that just something that they use heuristically to figure out which types of features seem to be useful, or do they do another optimization step over the types of features that they ask from you?
Sure. I guess I can answer these 2 questions together. So about the result of optimization, we do see great gains in the units of megawatts and the petabytes. And for example, maybe we are maintaining a lot of databases, say, on the left-hand side. And if using this lineage tracing, we identify that there are some tables that are not actually used by any models, then maybe we can just deprecate that and save some storage space. So that's one thing. And the other is definitely you have many features that you identify the duplicate computation and to save some electricity to compute them. So does it answer your question?
I guess I was interested in what percentage of the cost does it? Like, did you
do
any measurement of it?
Yeah, I think I saw the number somewhere. I don't recall the numbers right now. Let me think about that and get back to you.
Got plenty of time, so.
Just a quick follow-up. It looked like maybe the normalization step would do query optimization, or do I misunderstand?
Yes.
So that would be also a optimization benefit, efficiency benefit.
Sorry,
Thank
can you ask your question?
So the normalization would produce a more efficient query to the database. So that's also a gain from the system.
So we just store the normal forms of these features, say physically somewhere, and when someone tries to understand the features, we just query those.
I've got one. What's the biggest remaining pain point that this doesn't solve for you?
So the biggest, so this compiler project started a long time ago, and when it was designed, it was Oh, another benefit of functional programming I should brought up is pattern matching. Like currently, most compiler rules are still written in this form of graphs. So basically, the IR, the intermediate representation of the compiler, is kind of like a C-ish or Python-ish graph. You first have this graph node, and in the node you just embed an operator. Inside the operator, you embed some expressions, and so it makes each compiler rule. I mean, to describe each compiler rule, you just write a lot of code. And so because you have to find the graph and find the relations, unbox the node, and then put the box back, something like that. So one thing we are trying to do now is to make it more functional for the internal compilers. So like we just do pattern matching, and so one line can solve a problem 100 lines. So that's kind of the major project we are thinking about.